right in saying, haven't I, that in the cryptography lectures you've already been using modular arithmetic, yeah? Addition and multiplication modulo n. So that's certainly one piece of motivation for why we might study modular arithmetic and this congruence relation. The other, but in general, it's a very important concept in number theory, and I think the main idea to keep in your minds about what's going on is when we consider looking at the integers modulo some numbers. In the cryptography, you've been looking at the modulo 26 or whatever. What we're doing is we're taking the infinite set of integers and we're placing them into a finite set of, just use this informal word, a finite set of buckets for the moment. Okay, so you've got this infinite set of integers in which there's an infinite number of things. And what the congruence relation allows you to do is sort them in such a way that you've only got a finite number of things to look at, a finite number of buckets. And there are convenient labels. I mean, we'll get into this in a moment, but there are convenient labels consisting of 0 through n minus 1, to which we can label these buckets. And this can often be a good way to look at the integers and can often allow you to prove things about the integers. One example, one key kind of classic example of that is in the tutorials last week. We looked at this problem to prove. We looked at this problem because we want to prove that if p is prime, then p squared plus 2 is not. This is quite an interesting result. It's not immediately obvious by any means. There's no simple reason to explain why it's true. So whenever p is prime, then the number p squared plus 2 is not. But we were able to prove this by considering the integers z modulo 6. So that would have given us 6 buckets labeled 0, 1, 2, 3, 4, 5. But because p was a prime number, bigger than or equal to 5, so it doesn't work for 2 and 3. We considered the integers modulo 6, and we found that p was either 6 cubed plus 1 or 6 cubed plus 5. Those were the only 2 possibilities for a prime number. So what we were saying is in the 6 buckets that we have modulo 6, you only find prime numbers in number 1 and number 5 if you're looking at modulo 6. Okay. So the infinite number of prime numbers that there are, we were able to classify the integers in such a way that we only had 2 cases to deal with, a finite number of cases. 2 cases to deal with. And then we proved this result then by using this representation 6 cubed plus 1 and using the representation 6 cubed plus 5, using that directly to prove that this number p squared plus 2 was never a prime number. We could always factorize. So that was a nice piece of motivation. We should take that as being quite persuasive that this might be a useful way of looking at the integers. So let's meet the definition. I should have gone through the definition maybe before discussing some of this, but so it's a relation on the integers. We're going to write it using this 3-line equal sign, this equivalent sign. And the relation, and remember, a binary relation like this is a logical statement. It's something that's true or false. Okay? So we're defining a new relation here, like equals or less than or greater. Okay? It's a new relation. You give it a pair of inputs A and B, and well, n is understood to already been given. When you give it a pair of inputs A and B, it gives you a statement. A is congruent to B modulo n, and this is something which is true or false. Now, when is it true or false? How is the statement defined? Well, we say A is congruent to B modulo n if and only if n divides the difference. Okay? If only if n divides the difference A minus B. If A and B, the distance between them along the number line is a multiple of n, another way of saying it. And the notation we're going to use, we're going to write A, 3 line B, modulo n. You're going to read that in English as A is congruent to B, modulo n. A is congruent to B, modulo n. If it's not the case that A is congruent to B, modulo n, if n does not divide that difference A minus B, then we write, just in the same way you write unequal, so it's an equal sign with a line through it, we're going to write uncongruent, if you like, with the congruent sign with a line through it. Now we're going to make some remarks about this definition. First of all, it's just to note that it doesn't make a difference if you mix up the order in which A and B come, because remember, n divides the difference A minus B if and only if n divides the difference B minus A. So there's nothing crucial going on in the order in which you look at the difference, okay, because these numbers are just negatives of one another. So A minus B is equal to minus B minus A. And divisibility is, divisibility doesn't look any different when you look at it on positive or negative numbers when you change the sign. If n divides A minus B, it's certainly going to divide minus B minus A. What's the same thing? If n divides x, if and only if n divides minus x. Okay. So there's no problem with, there's nothing crucial involved in the order. And then the first result, let's just give some non-trivial examples. E.g., if we're talking modulo 6, maybe just to match it to this example with the numbers we were just talking about, then we will, of course, write things like 1 is congruent to 7, modulo 6, 3 is congruent to 9, mod 6. A few other examples, minus 5 is congruent to 1, modulo 6, etc. Okay, holds for positive integers and negative integers as well. Okay, and these are all true because when you look at the difference between the two numbers, it's some multiple of 6. Let's give a negative one. 15 is not congruent to 22. Because the difference between 15 and 22 is 7. So it's not multiple of 6. Now, the first result we're going to look at is theorem 4.1. And this is important. Indeed, some authors might even give the statement involved in theorem 4.1 as the definition of congruence. So if you like, it's like an alternative form of the definition. And this says that A is congruent to B modulo n. This is a very good way of thinking about it, and it ties in with this finite set of buckets idea. If and only if A and B leave the same remainder after integer division by n. Okay. So remember, we introduced this operation of dividing one integer by another. It'll go in a certain number of times, and you'll be left with a small remainder. Okay? But the remainder is the smallest positive number that you can have. Okay? It's going to be greater than or equal to 0. It'll be non-negative, but strictly less than the number n that you're dividing by. So two things are congruent if and only if they leave the same remainder after division by n. You can certainly see that here when you divide 9 by 6. 6 goes in 1 times with the remainder 3. When you divide -5 by 6, it goes in -1 times. Give you -6 with the remainder of +1. When you're doing integer division with remainder, the remainder has to be a non-negative number. So if you're dividing negative numbers by 6, you always take a multiple of 6 that takes you just to the left of the number, and then the remainder is the small positive hop you have to take to get back to the number. Now, what's involved in the proof of this? Well, it's written out in detail in the notes, but we can sketch the main parts of it here. It's a left to right. It's a if and only if. So there'll be two kind of directions to prove. But so if we assume the left-hand side, if we assume that A is congruent to B modulo n. Now, before we find out about what the remainders look like, we should just assume that A and B, when you do integer division of them by n, they're going to go in a certain number of times, Q1, Q2, and you'll have 2 remainders, R1 and R2. And the properties that these remainders have is that they're both non-negative, but strictly less than n. Okay. Now we're trying to prove that R1 is equal to R2. But what does this assumption of this, that A is congruent to B means? Well, we know that n divides the difference A minus B. So that implies that n divides Q1n plus R1 minus Q2n plus R2. That's just substituting in their integer divisions with remainder. But we can reorganize that in a sensible way, because this is going to be Q1 minus Q2 multiplied by n, and then it's going to be plus R1 minus R2. So now the statement we're looking at says n divides this multiple of n plus this bit here. But of course, we know that n divides this number here, this first term, because it's written as a multiple of n. So clearly, n divides the first part, Q1 minus Q2 n. So therefore, it must divide the difference between these two. We know it divides this whole quantity here. You can see that it divides the first term, so it must divide the difference of them. In other words, n must divide R1 minus R2. The justification for that, you see, because we've formed the difference between these two quantities, this line minus this quantity. So what we're making use of there is all the way back in Chapter 2, this was theorem 2.1. This was this long list of basic properties of divisibility. And it was part 3 of that, which was the divisibility of linear combinations. That if n divided x, to remind you of what that was, I might as well remind you on the screen. This was that if n divides x and n divides y, this implies n divides any linear combination of x and y. So if n divides x and n divides y, n is going to divide alpha x plus beta y for any alpha and beta. Well, the particular linear combination we're looking at here is just subtraction. 1 times this plus minus 1 times that. Okay, so remember, we're trying to prove that R1 equals R2. Now we know that n must divide the difference between them. So you can think of this along the number line. The distance between R1 and R2 is a multiple of n. Okay. But we know a lot about R1 and R2. We know that they're between 0 and n. Okay. Strictly to the left of n, but greater than or equal to 0. So if you think of your integer number line here, Okay, I know R1 and R2 are living somewhere in that range. So the furthest they can be apart from each other, if R1 and R2 are just living in this range, the furthest they can be apart from one another is really n minus 1. That's the maximum possible integer distance you can put between R1 and R2. Okay, so they're both strictly less than n, so they can't be up here. So since both of them are non-negative and strictly less than n, we know that the difference between them, so we don't know which one is the larger one, but the difference between them is, sorry, going to be strictly between n and minus n. So minus n is strictly less than the difference, and the difference is strictly less than n. But we also know that the difference is a multiple of n. So which multiple of n is contained in this range here between minus n and n? There's only one, n is 0. And the 0 is a multiple of everything. So the only possible value for this quantity here is 0. That's the only value in this range that is divisible by n. Everything is divisible. Everything divides 0. 0 is divisible by n. So it must be that R1 minus R2 is equal to 0, i.e. R1 is equal to R2. So that tells us that two things are congruent. They have exactly the same remainder after division by n, if they're congruent modulo n. Now, for some people, this is actually the definition of congruence. They say two things are congruent. What that means is they leave the same remainder after you divide them by n. So that's one way of saying it. The other way of saying it, as we've laid it out, that two things are congruent mod n if the difference is divisible by n. And they're really very close, as this shows. Okay, there's the other direction left to prove as well. The other direction, I think, is easier. The other direction becomes easier if we assume that when you divide them by n, they leave the same remainder. They leave the same remainder. So we've got some remainder r. There's no subscript 1 and 2 now. We're just assuming it's the same remainder. Yeah? It's the same number here. Well, in that case, if you look at a minus b, it's q1n plus r minus q2n plus r. The r's cancel out, and you've got q1 minus q2 multiplying n. Is that divisible by n? Yeah, obviously, because it's already factorized as something times n. So it's clearly divisible by n. So that's the other direction of the if idea. So that concludes the proof of that. Any questions or queries at all at this stage? So we've just met the definition. We've looked at some basic examples. And we've seen this equivalence now between saying two things are congruent mod n. That's the same as that they have the same, they leave the same remainder when you divide them by n. Okay. Any questions at all? Anything I can clarify on that? Okay. Okay. Now, this kind of picture, or this kind of main idea that we're taking the infinite set of integers and collecting them into a finite number of buckets, we just want to make this talk a little bit more precise and a little bit more correct and formal and use the correct terminology. So that's what's in the next section about equivalence relations. So really, we're dealing with two equivalent things, if you like. Equivalence relations / slash partitions. So these are two different two seemingly different ideas, but really they're two ways of looking at the same thing. These are logically equivalent ideas. So now you met equivalence relations last year in your decision maths unit, but an equivalence relation tilde on any set X, so we'll just talk a bit generally now, then we'll apply it to our congruence relation. So an equivalence relation is a binary relation on X. So if you're given two elements A and B from the set X, A tilde B is a statement, so it is either true or false. Just like our statement here, which was n divides A minus B, B minus A. It's not something that has a value. Well, it is. It doesn't have a numerical value. It has a logical value. It's either true or false. It's a statement. It's a declaration. So here we're talking about, so this is the character tilde. This is traditionally used to represent an abstract relation, a general relation. So, well, an equivalence relation is something quite strong. An equivalence relation is something which satisfies three key properties. These are the three key properties that make this relation mimic or act a lot like equality. Equality is the kind of fundamental relation. Two things are related if and only if they're actually equal, the same thing. Well, we're not saying that all the integers in this bucket corresponding to 1 modulo n, we're not saying they're all the same. We want to say, because they're not, they're all different things. But we're saying they share something very strong, they're equivalence. So any relation that satisfies these three properties is going to act a lot like equality. For that reason, they're called equivalence relations. The first property is the reflexive property. And that means for every element X in the set, X is equivalent to itself. Okay? So this relation, whatever it means, it relates everything to itself. Okay? This is true for our relation, since does n divide A minus A, i.e. does n divide 0? Yeah, that was a basic property of divisibility we looked at. Everything divides 0. So any relation which is like this, which says that an element is always related to itself, that's called a reflexive relation. The other key property is symmetry. Symmetry says, whatever goes one way, it goes the other way. So it's saying for every pair of elements in the set, if X is equivalent to Y, that's going to imply that Y is equivalent to X. Okay, our relation is equivalent to, because if n divides anything, it's going to divide minus that thing. N is going to divide B minus A, so the congruence relation goes the other way. Of course, not all relations are symmetric. The most obvious example, if you look at the strictly less than or strictly greater than relation, if something is strictly less than something else, the relation does not hold the other way around. 1 is strictly less than 5, but it's not true, 5 is strictly less than 1. So symmetry is a nice property for a relation to have. The other property is the transitive property. This says, a quote way of remembering this is that the relation travels through intermediaries. That's how I like to think of it. Travels through intermediates, i.e. for every triple of elements, X, Y, and Z, if x is related to y and y is related to z, so here y is the intermediate one. It's like the man in the middle, person in the middle. If x is equivalent to y, and in addition y is equivalent to z, then the relation, whatever this relation is, it somehow travels through y from x to z. So whenever you see a pair of elements equivalent like this, sorry, a pair of equivalences featuring the same y at the end of one and the beginning of the other one, we know we can travel all the way from x through to z, or that x is equivalent to z. X is related to z under this relation. Okay, so that's an equivalence relation. We're going to prove in a moment that our congruence relation is an equivalence relation. What's a partition? Partition is when you take a large set X. It's a really simple idea. It's very kind of fundamental, universal idea. You take a large collection of things and you divide them up into a collection of subsets. Just like it's a word used a lot in kind of international relations and politics. So the land masses of the earth are partitioned into nations, into nation states. Okay. So what's a partition? A partition of X. You've seen all this last year in decision. I'm just reminding you. Okay, well, I'm giving you the full story here anyway, so we're going through these things in detail. So what's a partition? A partition on X is a family of subsets okay, so they're a collection of subsets, x1, x2, well, okay. I'm kind of implying that it's a countable collection, that it is possible to index them with the positive integers, but we won't worry about uncountable partitions. But it's some collection of subsets, but they're arranged nicely. Basically, they account for all of X, so they cover the whole of X. And they don't, each cell, each subset is non-empty, and they don't have any overlaps. Okay, so you don't have any like little bit here which is in this one and also in this one. So they're completely distinct. So the three properties they have is for every I, xi is non-empty, not equal to the empty set. Second property is that the union over I of the xi is equal to the set X. So here I'm using the union operator like you use the summation operator or the product operator. Taking the union over the index I of all these sets xi is the union, x1, union x2, union x3, etc. Unioning up all the subsets, that gives you the set you're starting off with. And the third property is the no intersections property. But the way this is normally presented is there is a neat way to express this idea in a nice mathematical statement. We say, if it is the case that two sets, two of the subsets xi and xj, if they have a non-trivial intersection, if they seem to have an overlap, well, what's really going on there is that we're actually looking at the same set twice. The I is actually equal to j. Okay? So if you're looking at two separate sets, x1 and x2, if it's clear that the indices aren't equal, then the two sets have no intersection. Or equivalently, if I is not equal to j, that implies that the intersection is is empty. A question about the union. So, like in the same way that we write the sum of xi is equal to x1 plus x2 plus etc. etc. So in the same way, the union of a collection like that means x1 union x2 union x3 using the large union operator. Okay. So we've got equivalence relations and partitions, and they look on the face of it like they're two different things, and they are. One is setting up a logical statement amongst pairs of elements, a binary relation. The other one is looking at the large set and subdividing it in a careful way. But actually, the two go hand in hand all the time. Okay. So actually, these are, I hesitate to use the word equivalence because we're using it. These are equivalent constructions. What do I mean by that? What we mean is, if we have an equivalence relation, there's a very obvious partition we can build out of it. And on the other hand, if we've got a partition, there's a very obvious equivalence relation that we can build out of that. So if we have an equivalence relation, we have an equivalence relation tilde on X, then the set of equivalence classes so an equivalence class looks like, the notation we use is square brackets X. This is the set of every element Y in X, such that X is equivalent to Y. So you gather together all the things equivalent to X, equivalent to some named element little x. These are what the equivalence classes are. The set of equivalence classes, we collect together all the equivalence classes, they partition X. So if you've got an equivalence relation, you immediately have a natural partition associated to that equivalence relation. It's the partition formed by the equivalence classes. Secondly, if we have a partition of X, so you've got some splitting of X up into some collection of subsets like that, then there's an obvious, then the naturally associated relation where we say X is related to Y, so this is the definition of the relation. X is related to Y if and only if X and Y belong to the same subset. Okay, remember, to define a relation, a binary relation, you have to have a way of constructing a logical statement involving the pair, something which is true or false. This is the logical statement here. You say the statement is X and Y belong to the same subset. That's either going to be true or false. It's a very clear statement. It's not ambiguous in any way. If you know what X are and you know what Y are, you know what the definition of the subsets are, you can test to see whether X and Y are in the same subset or not. So this relation, the naturally associated relation, is an equivalence relation. Okay. So these two ideas of partitions and equivalence relations are linked strongly. Okay? They're really just kind of two viewpoints on the same thing. Okay? You can either think of it as a way of splitting up a large set into a collection of subsets, or as a way of introducing a formula, if you like, for a logical statement between pairs of elements on the set, satisfying these nice properties. Everything is related to itself, relations go both ways, and relations go through intermediates. Any questions about those definitions? So it's just a whole load of definitions.
In the box, is that general, or is that just a possible relation in the box?
Yeah, so, well, if you're starting from a partition, yeah, so this is one possible relation you might build out. But what I'm trying to say is this is a very, very naturally associated to the partition. If you've gone to the trouble of taking a large set, splitting it up into small compartments, yeah, why did you bother to gather all those elements together in one compartment unless you were going to say, well, there's some kind of equivalence or there's some kind of property shared by all the things you put in one compartment. So this is, if you like, the most natural relation you might associate to a partition. Two of the elements are related if they turn up in the same subset of the set. You know?
Confusing me that they're not the relation tilde, whatever it's not specific.
It's not specific because neither is the partition. I'm just talking about some spooky partition out there.
This is true or false, but we've not told you what the actual question is.
Yeah. So I'm speaking completely general there. Yeah. But to bring it crashing back down to ground again, something that is not completely general is taking the set of all the integers. So you've got an infinite number of integers here, the integers you know and love. You're considering the relation congruence modulo 6. So two integers are congruent if and only if their difference is divisible by 6. And the partition we are talking about, 1, 2, 3, 4, 5, 6. There's 6 compartments. And inside this one you'll find 0, inside that one you'll find 1, this one 4, this one 2, this one 5, this one 3. Okay. So immediately, if you start with this relation, you immediately generate this partition of the integers. Other things in here are 11, -1, -7. Yeah. Other things in here are 8, 14, -4. Infinite number of things in there. So if you start with the relation, you immediately just can't help but generate a partition Z. And by the same, going the other way, what is the partition of Z that generates this relation? Well, it's the partition where in one of the sets you find -7, 5, 11, -1, and all the other things that are. I mean, it's a bit difficult to say in a finite set of things because really there's no other way of saying it but just put everything in here, which leaves a remainder 1 divided by 6. Everything in here that leaves a remainder 2 divided by 6. And if you build that partition and look at the membership relation that it gives, so we say two things are equivalent if and only if they're found in the same subset, then that immediately is the congruence relation.
So,
question, Bruce.
Going from that, does that mean that all the subsets have to be the same size in the partition, or is there cases where they're varying sizes?
Well, are they all the same size here? Yeah, they seem to be. So the integers are countably infinite, and within each of these sets, there's a countable infinity of elements. So yeah, they are all the same size here. But no, I mean, there's no, that doesn't have to be true of any partition. Yeah. There's an infinite number of things in Z, and within each of these, there's an infinite number of elements. Yeah, certainly. So yeah, so this talk on the page, I'm speaking in general, just giving you the general definitions, the general setting. And this is immediately, couldn't be more concrete, because you're talking about one particular relation, one particular set Z, a specific partition. Okay, so the theorem then that follows there, theorem 4.2, is saying congruence is an equivalence relation. I'll be seeing you tomorrow with this as well, so we can get further and get towards some actual results here. But so having gone to the trouble of setting up this machinery of relations and partitions, congruence is an equivalence relation. Okay, once we know that, then we will know that we're on firm ground, that the relation we're looking at is one of these really, really nice relations. It acts a lot like equality, and it produces a subdivision of the set into a collection of subsets, and everything within one subset is strongly related to everything else. So how do you prove it's an equivalence relation? Well, okay, it's clearly a binary relation. Congruence mod n. So we'll fix an n. Congruence mod n, if you throw an a and a b at it, you get a logical statement. It's either true or false. That statement is n divides the difference. So it's clearly a relation between a and b. So to prove it's an equivalence relation, we have to prove that it's reflexive, symmetric, and transitive. So is it symmetric? Well, I've kind of already dealt with this. So from properties of divisibility, back in theorem 2.1, we know that n divides 0. But in that case, we also know that n divides the difference a minus a for any integer a. Okay, you can express 0 as a minus a, but if n divides the difference of a minus a, well, that's just the definition of a being congruent to a mod n. Okay. So congruence is reflexive. Everything is congruent to itself. Remember, this is the definition of congruence, a congruent to b mod n. The definition of that is n divides the difference a minus b. That's the definition. And I've already explained why it's symmetric. So from properties of divisibility, we know, same statement. So we're just basically taking the already established properties of divisibility that we have and translating them over into this new language. What do we know about divisibility here? We know that if n divides x, this is equivalent to n dividing minus x. That's true for any integer x. Well, that's going to imply that if n divides the difference a minus b, that's going to be equivalent to n dividing b minus a. Okay, because a minus b is just the negative of b minus a. So that is going to imply that if a is congruent to b mod n, because that's the definition of these two, that's equivalent to saying b is congruent to a. Okay? So it goes both ways. Congruence does. The last part is transitive. So for transitive, we should begin by assuming that a is congruent to b mod n and b is congruent to c mod n. Well, that means n divides the difference a minus b, and it also divides the difference b minus c. Okay, that's just the definition of what we mean when we say a congruent to b and b congruent to c. And again, it's an already established property of divisibility, but it then divides two things. It divides any linear combination. And which linear combination are we going to use here? Which linear combination of this, A minus B and B minus C, we're going to use? Just add them. What happens when you add them? A minus C, yeah. B's cancel, and you just get A minus C. And of course, that's the definition of A being congruent to C mod N. So it's automatically transitive. If A is congruent to B and B is congruent to C, it must be that A is congruent to C. So the congruence travels through intermediates. So this mod N is an equivalence relation. So this just puts this picture on this picture here, we sketched out for the example of n equals 6, puts it on a firm footing. Congruence modulo 6 is an equivalence relation. It acts as much as it can like equality. And we've got a very nice partition of the integers to 6 subsets when we consider the integers a modulo 6. Okay, so notice that, you know, this is kind of a concept you've been using a lot in the cryptography, but here we're just being very careful just to set it on very, very firm ground. Very careful with the definition and prove some seemingly obvious, I mean, you might have argued, oh, this is all obvious, yeah, it's obviously symmetric, it's obviously transitive, but we've been very careful to really rigorously prove that it is. And, you know, we'll continue this when I see you tomorrow. We'll introduce the operations of addition and multiplication and set those on firm ground too. Okay?